So here in section 8.3, we are going to use a p-value or probability approach to hypothesis testing. So this p-value, also called the observed significance level, for a specific statistical test that you perform is the probability that, assuming H0 is true, that you would observe a value of your test statistic here that is as extreme or more extreme than the actual value that you get from the sample data. So your p-value is measuring how much your null hypothesis disagrees with the test statistic. And smaller p-values mean more disagreement. Geometrically here, your p-value is the area past the test statistic. So remember that alpha is the area past the critical value. So this is slightly different. Which again is the probability that you would have a test statistic that is as extreme or more extreme than the one computed from the sample. So here's how you make your decision with the p-value approach. So your p-value you can think of as the smallest alpha that you would use and reject H0. So if p is less than alpha, you reject H0. And if p is greater than alpha, you do not reject H0. So you accept H0. So let me illustrate with an example here. So going back to our lead in the drinking water example, we had 30 randomly selected schools. We were testing to see if the level was greater than 15. Our sample mean was 16.2. Our standard deviation 2.4. Alpha is 0.05. So our H0 was mu equal 15, our HA was mu greater than 15, and then our test statistic was 2.74. So here is our distribution curve for the X-bar distribution, and then 2.74 would be way out here. So that is our z-test is 2.74. And then that little sliver of area past that, that's the p-value for this upper tail test. For a lower tail test, it'd be below on the lower side. So our p-value is going to be the probability that z is greater than 2.74. And since this is a normal distribution, we can compute that with normal CDF. So we can do normal CDF. Our lower cutoff, 2.74. Our upper cutoff, infinity, we'll use 10,000. We're doing z-scores, so mean standard deviation are 0, 1. So let's check that. So second variables to get to our distribution menu. Number 2, normal CDF. Lower, 2.74. Upper, 10,000. Mean standard deviation, 0, 1. So 0.0031, usually do those on 4 decimal places. So equals 0.0031. So then our test result then, now that we've calculated this p-value, well, we notice that that p-value is less than alpha. So our p, which is 0.0031, is less than 0.05, which is our alpha. So we reject H0. And that's what we did when we did the classical hypothesis test with rejection region. So notice we didn't sketch our rejection region here. But the reason that you reject when p is less than alpha, so this p, that's area 0.0031, and then the alpha is 0.05, that's the area past the critical value. So if I graph that rejection region, it would look like this, and then alpha would be the area past that, that's our 0.05. So if the 0.05 is bigger than the p-value, that means that your test statistic is past the critical value. So here our value for z 0.05 was 1.645. So 2.74 being greater than 1.645 is the same as saying that the p-value is less than alpha. So, and then our interpretation here is that there is sufficient evidence to conclude that the mean is strictly greater than 15, which is our alternative hypothesis. So the only thing that changes in there is the step after the test statistic. When you're determining the result, you use the p-value to do that. So determining the statistical result. And then you've got the added step of actually computing the p-value first. So if we go back up to our steps in a hypothesis test, step 4, compute the test statistic. Step 5, instead of test statistic falls within the rejection region, it's going to be compute the p-value and p less than alpha. So that's the only difference between these two methods of hypothesis testing, is that step 5.